So, after I've described in a simple way the main concepts about electrical double layer, it's important to describe which are the different types of model used in order to describe what is happening due to the creation of an electrical double layer. And the model that we will see are, in particular, the first one, the holder, that is the Helmholtz model. Then we will see the Gouy-Chapman model, the CERN model, and the Graham model. So we need to start now from the older one and arriving increasing the number of assumptions and increasing step after step the complexity of the surrounding condition from the older one, the more simple, to the more interesting. Nowadays is the Graham model that taking consider about a quite high number of parameters with respect to the Helmholtz one that is based on a lot of assumption and approximation. So basically now let's start with the descriptions of the Helmholtz plane. So in general, why we want to describe different models, but it's quite simple, because basically in a way in which we have an electrical double layer, for instance the situation that we have described in the during the last lessons, we have, for instance, one electrode, the correlated circuit, and the presence of the medium, the electrolyte. And we know how this type of situation lead to the generation of a negative surface excess and the corresponding compensation mechanisms due to the migrations of cations under an electric field. So the point basically is that since we have an electric field here and since we have a certain charge excess, our electrodes are characterized with a surface potential. So we have a surface potential that is able, a single parameter, to quantify the polarization of this electrode. And since moving from the surface toward the other electrode, what is happening is that basically we can have a compensation due to the presence of positive charge. And this compensation leads to a decrease in the potential. So the potential, not the surface one, but the potential as a function, is a function of what? Is a function of the distance between the surface, the distance from the surface of the electrode toward an hypothetic infinite distance from it. So basically, the reasons for which we are so interested in the modelizations of an electrical double layer with different types of model is that different models based on different assumptions are able to provide different information for the resolution of this function. So the final aim is this one, is the resolution of this function. The final aim for a physical description and characterizations of an electrical double layer is try to understand in which way the potential is changing, increasing the distance from the electrode, or in general the distance from the surface excess. It could be an electrode, it could be a particles, for instance in this disperse system. So basically we want to solve this function. We want to describe this profile, and we can do this only if we are able to design a specific model with specific conditions. And so we can start from the older one, the Helmholtz double layer model is the simplest. It's the simplest because in this case we are treating the electrical double layer as a plate capacitor. So let's focus our attention on the Helmholtz electrical double layer. So in order to solve this function, the electrical concerning the electrical double layer potentials profile, the Helmholtz model, that is the simplest and the older, try to describe the double layer as a sort of plate capacitor. What does it mean? If this is our electrode or our, in general, body having a surface excess, now, obviously I speak a lot about electrode since we are dealing with electrochemistry, but it could be everything able to charge, to undergo with a charge acquisition mechanism. Since the Helmholtz model described the double layer as a plate capacitor, we are imagining that after the movement of cations due to the electric field created with this excess, all the positive cations and so all the positive charge is bounded and completely localized in a single mono layer. So we are imagining that basically all the previously randomly present cations have migrated in this direction. And after this, we cannot appreciate anymore any presence of further cations in the bulk, but all the cations are localized here, in a single layer. And what does it mean? That the compensation mechanism, so the way in which the surface excess is balanced, is completely localized in this region. Is a sort of plate capacitor in which we know what is a capacitor, an electrical device in which we can store energy electrostatically. And so basically what is happening in the case of a plate capacitor is that we have a negative excess of charge present on a plate, on a conductor plate, we have a dielectric, and we have the corresponding positive charge in the opposite plate. So basically the concept is the same, and since the concept is the same with the Helmholtz model, we are imagining that the electric field is completely localized only in this region. And so, what does it mean? That from this point of view, we can have a function, distance and potential, that this is the starting point, the surface potential, the one that we have described previously. What is happening is that since the electric field is localized only in this region, we have a decrease in the potential until to reach a minimum, and then this is to remain constant, since we do not have any additional positive charge. And so we have this profile, so a decrease in potential is completely localized in this zone, since we are behaving as a plate capacitor. But this model have a lot of problems. Because this resolution, yes, it's quite interesting, but we are not considering, for instance, the molecular nature of the ions. We are not considering the molecular nature of the solvent containing the ions. When we are even not considering the thermal motion. So there are a lot of approximations, reason for which these types of profile is not really precise, and we need to pass from the Helmholtz model to the Gouy-Chapman. So let's try with descriptions of the second type of model, the Gouy-Chapman. So the Gouy-Chapman model is a more smart types of model that allow us, with more precise surrounding condition, to have a more clear idea on in which way electrical stable layer is created. In particular, in this case, the assumptions that is present in addition with respect to the Helmholtz model is that we are considering also the thermal motion of the ions. And so we can have an absorption energy due to the presence of the electric field, but we can even have a thermal energy due to the Brownian motion. And so we have basically something that tries to take our, collect our ions and bring these ions reaching and push these ions toward the electrode. But we have even some thermal energy in which these random movements, statistical movements, are able to promote the movement of ions at the same time far away from the electrode. So we have to take in consider also the presence of thermal energy. We have the electric field, but we even have another contribute that can avoid the perfect collections of positive charge in a single layer. Basically, what we are doing now is that if the absorption energy is quite close with respect to the thermal motion energy, we have our well-known situation. But since we are now talking about a balance between the absorption energy and the thermal energy, it's true that we have a high concentration of positive cations here in order to compensate the surface excess. But at the same time, since we have a thermal motion trying to push cations even in the opposite direction, this compensation mechanism is ensured only for infinite distance. What does it mean? That the amount of positive charge, even if is more present when we are close to the electrode, is localized in an infinite layer. So basically, obviously, here we have their concentrations, and moving away, we are basically even we have smaller concentrations of cations, but the total electroneutrality is ensured only for infinite distance. Because we have the absorption, but we have the thermal motions, and so we have just a statistical distribution of cations in each single point, in each single distance. So if we want to describe this concept from in terms of functions, potentials versus the distance, we can say that in this case we have a diffuse layer and an exponential profile starting from the surface potential and reaching infinite distance. We have a diffuse profile. We can see that the electric field is not totally localized here, but we have the presence of charge that are present even in a real far distance, even if obviously the concentration it will be really small. So basically, what is interesting here is that in the diffuse, these types of model is described with a function that is taking consider about the Poisson equation and the Boltzmann equations that are collected and with specific resolutions, with specific surrounding conditions, lead to the well-known Gouy-Chapman equation. So the Gouy-Chapman equation basically is an equation that describes which is the exponential profile of this function. So if we are able to collect all the information associated with this model, so the presence of thermal energy, the press, and in general also the fact that we are in equilibrium condition. So we are considering that in each single point, since we are in equilibrium, the contribute due to the diffusion is completely balanced due to the contribute concerning the migration. What does it mean? That we can say that if we are in equilibrium, that in each single infinitesimal plane, each single charge can feel the presence of the electric field and want to move in this direction, but at the same time, under a concentration gradient, it feels the lack of cations in this point, we respect this one, and so the diffusion pushed the cations in the opposite way. So we have the migration that try to push these cations here, but the concentration gradient, diffusion, try to push it in this direction. And so at the equilibrium, the migration and the diffusions are completely balanced. And so this is another important surrounding condition in order to reach the mathematical resolution of the Debye-Hückel equation. That is the function describing this profile. So obviously this parameter is the surface potential, the potential associated with the surface of our electrode, for instance. This is the distance, and this is the Debye length, the Debye length that is a parameter that is able to quantify the thickness of the electric acid double layer, basically. And it's extremely important, for instance, in formulation, because it is a function of a lot of interesting parameters. For instance, the nature of the solvent, the permittivity, but is a function even of the temperature, is a function of the valence and the concentrations of electrolyte, and a lot of other parameters.